Hi, it's me, Alwyn. Today I'm talking about the freefall time. The freefall time tells us how fast an object collapses if nothing is there to stop it, such as internal pressure. And this is really exciting because many of the things we care most about in the universe rely on gravitational collapse in just this way. For example, clouds of gas within the galaxy turning into stars, or stars at the end of their lives collapsing into neutron stars or black holes. Before I talk about the freefall time, I will have to talk about acceleration over a distance because gravity causes things to accelerate, and that will be the primary tool we use to relate acceleration by gravity, distance, and time. I've been excited to make this video for a while now because I've been working on the freefall time on a research level for 3 years, and I've been trying to figure out how to explain the freefall time in a simple and intuitive way without using calculus as much as possible. Let's talk about constant acceleration. So let us first have time, and we will start from 0, and we will just put in all of our times up to 13, because that is as high as I can count. And let us have some acceleration, and we will just have a constant acceleration of 2 so that we can gain some intuition for what constant acceleration does. Next, we will have velocity, and we will start velocity at 1, and we know that it will increase by 2 each time. Now we will have distance. So this is the distance that we travel. And this estimation of the distance will just be based on the previous velocity. And we'll start at a distance of 0. And then 1 plus 0 is 1. 3 plus 1 is 4. 4 plus 5 is 9. 7 plus 9 is 16. 9 and 16 make 25. 11 and 25 make 36. 13 and 36 make 49. 15 and 49 make 64. 17 and 64 make 81. 19 and 81 make 100. 101 and 121 make 121. 121 and 23 make 144. 144 and 25 make 169. Basically, at each time, we assume we are moving at velocity 1 for the next entire time unit. So for example, if our time unit was seconds and our velocity was 1 meter per second, then after 1 second we move 1 meter. So our distance accrued is 1. And then the next second we will move 3 meters because our velocity has become 3. So then our next distance will be 4. Now, you may have noticed a pattern already that the distances compared to the times here are the square of the time. And you might think, what a interesting pattern, what a strange coincidence that all the distances happened to be square numbers. Well, in this case, it's because I chose an acceleration of 2. So, well, it's not really because the acceleration is 2. Intuitively, you can think of this as the more time that passes, the more time you have to build up speed, and the more time you have to turn that speed into distance. So if velocity is equal to acceleration times time, then distance ends up being related to the time squared. And logically, we also know that the faster our acceleration is, the faster everything should go. And we can see in this case, it turns out that it's 1/2 times the acceleration times the time squared that becomes our distance. And so even though I have not derived for you using calculus that this is a typical expression relating acceleration, time, and distance, you can sort of see, based on this simple example, that the more time that passes, the more velocity you pick up, and the more time you have to turn that velocity into more distance. And so that's why it's time to the second power, or time squared. Okay, we can also consider dimensions. An acceleration is usually measured in meters per second per second. For example, if you have a velocity in meters per second, then you want to know how many meters per second you add in velocity every second. So that's why it's meters per second per second. And we know meters are a distance and seconds are a time. So putting together acceleration, distance, and time, you have to put them together in such a way that the units work out. So an acceleration is a distance per time squared, a meter per second, or a distance per time, distance per time squared. And when you move the time to the other side to be with the acceleration, then you get distance is acceleration times time squared. And as we saw previously, the distance is 1/2 times the acceleration times the time squared, or d equals 1/2 at squared. And if we want to figure out how much time it takes to travel a distance d when you have an acceleration a, again, you just move things around. You move the 2 to be next to the d, so 2d. You move the a to be under the d, and then you have 2d over a, and you take square root of both sides in order to have t equals 1/2 square root 2d over a. Now let's add gravity, because that's the other part of free fall. It's not just acceleration, it's acceleration by gravity. We know that the more massive something is, m, the more acceleration by gravity you feel. And the further away you are, the less acceleration you feel. So this is the equation A equals gm over r squared, where g is Newton's constant, because Newton had the bright idea of understanding that gravity was between two masses. Now let's imagine that we're just one small point of gas on the very edge of a ball of gas. The thing is, all of the inner points, they will be falling inward faster than us because they are closer to the mass inside. And the thing is, there's not really a reason we should expect that our furthest out point should be faster than any of the inward points. So we should just assume that the outermost point, when the outermost point shrinks, that determines the whole thing shrinking. So we'll just think about the outermost point. The outermost point has a gravity that's based on how far it is from the center of mass of this whole ball of gas. And that is just from the center of the ball to the edge of the ball. And that's just the radius. And the mass that we have to consider is just the total mass of the ball. Because it's the outermost point, it cares about everything. All of this stuff is pulling this point towards the center. Now we will make some approximations, and we will pretend like we are just collapsing the ball of gas by some small fraction. And the reason we care about collapsing it by some small fraction instead of all the way to 0 is because the first part of the collapse will be the slowest part. We know that the collapse will get faster and faster as the ball gets denser and denser, as the force of gravity gets stronger, because if you remember, gm over r squared, when r is smaller, the force of gravity, when the distance to the center is smaller, the force of gravity is much bigger. So once we start collapsing, it just gets faster and faster. So the later parts of the collapse are going to contribute a very small amount of time because they will happen so quickly. They'll pass by very quickly. The slowest part that we have to care about when calculating the time is just the first a little bit of the collapse. So the distance we'll try to move is just a small fraction of the total size of the object. So now we will start putting together everything we know. We talked about just now that the distance we want to move is some fraction times the radius of the object. We know the acceleration of the outermost point is going to be g total mass over total radius squared. And we know how to get a time from a distance and acceleration. All we have to do now is put everything together and plug everything in. So d gets replaced with f and r, and we flip the a gm over r squared upside down, so the r squared comes up to the top and the gm is on the bottom, and the r squared and the r from d combine into r cubed. And now we can do a little bit more, because we can remember that the volume of a sphere is 4/3 pi r cubed, but I'll ignore the 4/3 pi, and we'll just think about the radius cubed. We know that a mass per volume is a density, and here we denote it by the Greek letter rho. So it turns out that knowing that the mass per radius cubed is a density, and we have the same thing here in the time, now we know that the time just depends on the density of the object. And this is the power of the freefall time. Once you know the density of something, you know how quickly it will be able to collapse, assuming that only gravity is working on it and there's nothing stopping gravitational collapse, that it's free to fall. It turns out that for a sphere, the true answer using calculus is this complicated thing. But we got quite close just by considering dimensional analysis and allowing it to collapse by a small fraction. If you add together many small fractions, what ends up happening in calculus is you get the true numerical value of 3 pi over 32. But the most important thing to remember is this dependence on the density. The denser you are, the bigger your number on the bottom is. So the denser you are, the faster you will collapse. And this is intuitive. Intuitively, the denser something is, the closer together all the mass is. So you know that the gravity will be much stronger. Okay, so just to wrap up, we derived what the freefall time is, which gives us a way to estimate how long it'll take for something to happen. For example, how long it will take for a molecular cloud of gas to turn into a star, or how long it will take for a star to turn into a neutron star or black hole. It also gives us a way to compare, for example, the freefall time of an object versus the sound crossing time for an object. So if you're on one side of the object versus the other side of the object, if you want this side of the object to send a pressure wave to this side of the object, it will take some time because pressure waves travel at the speed of sound. So that's the sound crossing time, the time it takes for pressure waves to go from here to here. If the pressure waves cannot make it in time from here to here, and the freefall time is shorter, then what ends up happening is that gravity is stronger than pressure, and so then you would have collapse. When you have a near equivalence of freefall time and sound crossing time, a near equivalence of gravity and pressure, that's what's called hydrostatic equilibrium, a balance between gravity and pressure. For my research, I studied how the freefall time might tell us how quickly molecular gas clouds can form stars, because it tells us how quickly those gas clouds should collapse to form stars. Thank you very much.